Looking at one last way to factor, we can still factor if we have x to the fourth instead of x to the second. So when we have degree 4, we're going to look at two special cases with degree 4. One where we have a trinomial with x to the fourth plus bx squared plus c. Notice this is very similar to having x squared plus bx plus c. If I look at where does that x squared come from, well, we talked about how it's a binomial and it factors to put an x in the front because first times first gives me that x squared. Well, how do I get an x to the fourth? Well, what if I had a binomial? Because I know a binomial times a binomial gives me this trinomial. And instead of having an x in the front of each, I had an x squared in the front of each. Would an x squared times x squared give me that x to the fourth that I want? Sure. So all I'm going to do when I have x to the fourth plus bx squared plus c is I'm going to use factor sum tables just like I have with previous trinomials that started with just x squared. But now I'm going to put an x squared in the front of each instead of an x. I'm also going to have to make sure and always double check that this expression that I get in each factor that I get can't be factored further. And I'll show you what that means in a couple examples here momentarily. The other situation is if I have a to the fourth minus b to the fourth. Notice that's very similar to having a squared minus b squared. It factors in a very similar fashion. It's going to factor to b, and I should use a to stay consistent, so let me get that x off. It's going to factor to be a squared minus b squared times a squared plus b squared. So again, very similar to before. And again, then I always have to double check to make sure I can't factor further. So let's actually look at some examples here. So in the first example, I notice I have x to the fourth minus 8x squared plus 7. It's a trinomial that starts with x to the fourth. So I'm going to try to do some factor sum tables and see if I can't turn this into two binomials, both that start with x squared. So I'm going to do factors of 7 with a sum of negative 8. This is, remember, my table to do my guessing and checking. Well, I see that negative 7 times negative 1 is positive 7. Negative 7 plus negative 1 is negative 8. So I'm going to go ahead and say minus 7 minus 1. So now I have to check to make sure it can't be factored further. Both of my pieces are binomials, so I've learned a couple methods now to work with binomials. I've learned perfect square minus perfect square, and I've learned a cubed minus b cubed and a cubed plus b cubed. So perfect square minus 7's on a perfect square. Perfect square minus 1. Well, guess what? 1's a perfect square. So I'm going to go ahead and I'm going to factor this piece further. So this is just going to remain. So I'm still going to have x squared minus 7, and I'm going to use the formula that tells me if I have a squared minus b squared, so a is x, b is 1, that factors to be x plus 1, so a plus b, a minus b. There is my most factored form. Looking at example 2, I notice example 2 is very similar to example 1 because it is also a trinomial. It also starts with x to the fourth, so I'm going to try to put an, oops, not an x to the fourth, I'm going to try to put an x to the second, or x squared, in the front of each of my binomials and use a factor sum table to find what goes in there with them. So I'm going to do factors of the last with a sum of the middle. Just to point out, I did not put any of the examples in here, but if this had had a coefficient other than 1, I could also use the factor sum tables with grouping to help me in a problem like this. But going back to my the number 2, the original problem I have, factors of negative 10 with a sum of negative 3. Well, I know that negative 5 times positive 2 is negative 10, and negative 5 plus 2 is negative 3. So I'm going to go ahead and say minus 5 and plus 3, and then I check to see if it can be factored further. Well, I notice that they're both binomials. However, neither situation is an x cubed, and neither situation is a perfect square minus a perfect square. In both of these, I have a 5, which is not perfect square, and then I have a plus 3, which is adding in, not a perfect square. So whereas in the first example I could do more, this one I have to stop here. Looking now at the other situation, notice on example 3, it's in a little bit different form than the last two examples. This looks like it's in the form perfect 4 minus perfect 4, because I know that x squared times x squared is x to the 4th, and 1 times 1 times 1 times 1, or 1 squared times 1 squared, is 1. So I'm going to go ahead and let my a be x, my b be 4. Then using that formula, I'm going to have x squared plus 1 squared, which is just 1, times x squared minus 1 squared. I checked to see if this can be factored further. I noticed that this binomial here is in the form perfect square, subtract perfect square. So I'm going to leave x squared plus 1 alone. And x squared minus 1 is going to become x plus 1 times x minus 1. X squared plus 1 cannot be factored further because I can only use my formula if I have a subtract sign in the middle. So that is the best I can do there. Looking at one more example that's similar to example 3, I notice that x to the 4th, I can say, well, hey, my a is x squared, and my b is, well, 2 times 2 is 4, times 2 more is 8, times 2 more is 16. So, oops, my a is x, my b is going to be 2. And then using my formula, I'm going to get a squared plus b squared times a squared minus b squared. Well, that gives me x squared plus 4 times x squared minus 4. I recognize again that this is perfect square minus perfect square, so I can factor that further to be x plus 2 times x minus 2. Giving me my most factored form. So again, x to the 4th, very similar to some strategies we're using with x squared.